Hi, I'm Magnus Morton, and today I'll be talking about DelayRepay, delayed execution for Kernel Fusion in Python. All my co-authors and myself are at the University of Edinburgh in the UK, except for Christophe Dubach, who is at McGill University in Canada. I'll start with the executive summary. Can we use delayed evaluation to improve the performance of numerical Python workflows on GPUs? The answer is yes. I'll begin by talking about the context of what we're doing. Python is not a high-performance language, and is pretty unapologetic about that. Please note that I'm conflating Python the language and CPython implementation here. So really, CPython is what is not high performance, but for the purposes of this talk, Python and CPython are the same thing. In spite of this, Python is an extremely popular language for data scientists. Data scientists and numerical programmers use libraries such as NumPy, SciPy, and so on, which allow them to combine the user-friendliness, familiarity, and ease of Python with high-performance numerical libraries. We're also now in the age of heterogeneous accelerators. So, by heterogeneous accelerators, I mean GPUs, FPGAs, coarse-grained reconfigurable accelerators, and ASICs, and so on. Now, hardware like this can give extremely good speedups for certain types of programs. However, they can be painful to program, often requiring a programming model radically different for that from a CPU. This, of course, means that existing code has to be rewritten to use them. This is particularly bad for data scientists who may have little experience in writing low-level code or managing device interaction, and may be blissfully unaware that there are even such things as other programming models. Luckily, many people have attempted to solve this problem. There are many GPU tools and libraries for Python, and for other data science and numerical languages like R, Julia, and so on. But in Python, NumPy, PyCUDA, PyOpenCL, and CuPy are some of the most well-known examples. I'll focus in on CuPy a little bit because it's the most important of these, apart from NumPy, in terms of this talk. So CuPy is a drop-in replacement for NumPy on CUDA that does not have automatic kernel fusion. We'll be directly comparing our approach to CuPy as a competitor, but our tool also builds on CuPy. So many of these libraries require rewriting existing NumPy code, or they require knowledge of GPU architecture, such as the workgroup size, number of CUDA threads, things like that. Other, more drop-in libraries don't perform as well as they could. And part of the reason for this is that they do not have support for automatic kernel fusion. Now, kernel fusion is where multiple GPU kernels are combined into a single kernel. This can give significant performance improvements via locality improvement, reduced loads and stores, and simply less time spent compiling, because compiling one kernel is quicker than compiling 10, for example. As an example, here's a simple NumPy-like program that will assume is running on a GPU. So this program computes the Pythagorean identity, and it's an example we'll be revisiting throughout this talk. So without Fusion, we would need 5 kernel calls, 1 for each arithmetic operator and 1 for each function. With kernel fusion, we'd only need 1 kernel call for the whole lot. This would give us at least a 4 times speed up. So our solution to this problem is DelayRepay. DelayRepay is a drop-in replacement for NumPy, which improves performance over existing solutions for free using delayed evaluation and kernel fusion. Now I'll move on to the design and implementation of DelayRepay. So we want to gain the benefit of kernel fusion without changing existing code. This is a key goal of ours and is sort of critical to all the design decisions we made while building this. We want to replicate the NumPy API exactly and fall back to NumPy's actual implementations when we can't support a NumPy function for whatever reason. The only change DelayRepay requires from its users is a change in the import statements of the program. So, as an example, here on the left is a simple NumPy program, and on the right is the equivalent DelayRepay program. The only change is the import statement at the top. On the left, it was import NumPy, and on the right is now import DelayRepay. The rest of the program remains exactly the same. We thought that delayed evaluation may be a good way to achieve kernel fusion. By delayed evaluation or delayed execution, we mean that we will not evaluate parts of the program until they are needed. We are only delaying NumPy parts of the program, and any other Python gets eagerly evaluated. Doing this allows us to combine the NumPy operations at a high level and thus easily generate fused kernels. This avoids the need to fuse distinct CUDA kernels at the CUDA source level. To do this, we need to generate a delayed execution graph of NumPy operations. So we overload the NumPy array type and all the NumPy operations to return DelayRepay nodes. We essentially generate an abstract syntax tree of NumPy operations. Here's the earlier example again, showing how at each step we return our DelayRepay types and how each further step in the computation builds on the previous step, returning a more compounded DelayRepay type. We can see this more clearly when we look at the tree representation of the same computation. We can see how the higher level nodes compose the others. Note that both these NP array nodes at the bottom here are in fact the same node. So in order for this to be useful, we need to evaluate our delayed graph eventually. Evaluation is forced when a DelayRepay type leaves the DelayRepay context. So I'll give a quick list of when this might happen. So a print function, an unsupported NumPy function, conversion to a plain Python list, getting a string representation of the delayed object, a non-NumPy function or method, or a comparison function. This is a non-exhaustive list, but covers nearly all cases that we might see. Evaluation, of course, triggers CUDA kernel generation, compilation, and execution. Evaluation will return a NumPy array wrapped in our DelayRepay type, allowing the cycle to begin again. We use CuPy to generate CUDA kernels, and CuPy also manages device memory, data transfer, and scheduling. This saves a lot of boilerplate coding. The code is generated by walking our delayed execution graph and generating static single assignment expressions in CUDA. These SSA expressions are then spliced into a CuPy CUDA kernel template. We use aggressive caching to avoid revisiting nodes and to reuse existing fragments. This is self-contained within a single run and is separate from standard CUDA kernel caching, which we will use if it's available. We also do some other optimizations such as common subexpression elimination and something that I'll call scalar partial evaluation. Because this whole process is done dynamically just in time, we can treat scalar variables as constants and fold them into the generated kernels directly. As well as a possible performance boost, this avoids the need to transfer variables and avoids any hacks like wrapping them as single element arrays, which is relatively common when we're doing GPU programming. So now we move on to the evaluation of our delayed evaluation system. We benchmark DelayRepay against Kuba, Borium, and NumPy. Borium is a GPU library for Python which claims some support for kernel fusion. It's quite similar to Kuba, and then it's a drop-in replacement also. We use a suite of NumPy macro benchmarks, and they all are run on a server with an NVIDIA Tesla K20 GPU. So we do two different types of benchmarking runs. The first one, we measure the computational kernel time, meaning the time spent on device or in native code, and we try and measure that as tightly as possible, excluding all warm-ups, that sort of thing. And everything is aggressively cached here. And for the second set of runs, we measure the end-to-end, or the cold time, as we call it, which includes everything such as warm-up, virtual machine startup time, and all kernel caches are dropped before running. I think this is particularly useful to look at as users interact with Python programs interactively and will be modifying things as they develop iteratively. This is particularly important when people are using things like Jupyter notebooks. So let's have a look at the computational kernel, or warm times, to start with. So in this graph, blue is Kuba, orange is Borium, and green is DelayRepay. Each bar represents the speed up relative to NumPy, and this is a logarithmic plot. We can see that we almost always see a speed up for all of the libraries, except for a few slowdowns for Borium. We can see that DelayRepay almost always produces the best speed up. Using the geometric mean, Borium has an average speedup over NumPy of 11, Kuba 15, and DelayRepay the best with 24. Over all the benchmarks, Borium has a maximum speedup of 203, Kuba 74, and DelayRepay again the best with 377. For the cold, or end-to-end results, we see a different picture. Kuba and Borium generally produce a slowdown compared to NumPy. DelayRepay, on the other hand, produces a speedup on average. Again, using the geometric mean, Borium has an average speedup over NumPy of 0.37, which is a slowdown. Kuba 0.77, again a slowdown, and DelayRepay an actual speedup of 1.25. Borium has a maximum speedup of 3.85, Kuba 3.75, and DelayRepay 6.79. This chart here shows the memory usage of Borium and DelayRepay compared to Kuba. In most cases, we see reduction in memory usage, which you would expect when fusion is achieved. Note there are two cases where Borium appears to have memory usage of 0. This is to do with the failure to instrument Borium, where it crashed trying to instrument it. Okay, so we generally see a significant speedup for DelayRepay over Kuba, Borium, and NumPy, along with reduced device memory usage. We have one case, though, where DelayRepay makes things worse. This is a result of a program with many random constants being fed into our system, producing many kernels, one for each random input. In contrast, Kuba will only produce one kernel in this situation, whereas we might produce thousands. So the compilation costs here are enough to offset any benefits from fusion or from any other optimizations we do. But overall, DelayRepay performs very well. We have several ideas for future directions. We are looking at creating a Lift backend for DelayRepay. Lift is a functional intermediate representation and code generation framework. This will enable us to target other devices such as coarse-grained reconfigurable accelerators and allows further optimizations. we would like to add a heuristic or machine learning based decision system to the runtime. This would basically decide whether or not to even schedule at the GPU at all. So in some cases, it would fall back to NumPy if the conditions were not favorable. We'll be adding more support for further NumPy and SciPy operations. And finally, we would like to investigate how this technique could help improve performance on CPU only. So in summary, with DelayRepay, we have used delayed execution to enable kernel fusion on GPUs in Python. We have shown significant performance improvements without modifying existing code. Thanks for listening to my talk. I hope I've inspired you to read the full paper. I'll now answer any questions you may have.